Thanks for watching today. Today's topic: prediction and classification of series data using LSTM. Series data means sensor data, videos, anything that changes over time. LSTM stands for long short-term memory. It's a type of recurrent neural network, often used for time series or text classification. Before we dive in, let's do a quick review of neural networks. Before we go ahead, let's first look at what neurons are and how they work in our brain. Then we'll learn about artificial neurons. A neuron is the basic computational unit of the human brain. We have about 100 billion of them. Each neuron connects to others through synapses. Neurons receive inputs from the outside world or from other neurons through branch-like structures called dendrites. These inputs are weighted by importance, then summed together in the cell body, the soma. Finally, the result passes along the axon and is sent to other neurons. That's the biological version. Now, let's see how we mimic this in artificial neural networks. Now, let's see how artificial neurons work. Let's suppose we have these inputs, x1, x2, to xn to predict output y. These inputs are multiplied by weights w1, w2, to wn and are summed together. But why are we multiplying these inputs by weights? Because all of the inputs are not equally important in calculating the output y. Let's say that x2 is more important in calculating the output compared to the other two inputs. Then, we assign a higher value to w2 than the other two weights. So, upon multiplying weights with inputs, x2 will have a higher value than the other two inputs. In simple terms, weights are used for strengthening the inputs. After multiplying inputs with the weights, we sum them together and we add a value called bias b. Finally, we pass that sum through an activation function or transfer function, like logistic sigmoid, tan, or ReLU. This introduces nonlinearity. That's the basic artificial neuron. What's on the slide right now is a two-layer neural network. One layer, then a second layer. This network takes a four-dimensional vector as input, so four numbers go in, and it produces a three-dimensional vector as output. Three numbers come out. Now, the number of neurons in each layer here is 3. But it doesn't have to be 3. It could be 10, 100, 1,000, or more. So in this way, a neural network is like a nonlinear mapping. A vector goes in and a different vector comes out. That's basically how you can think of it. Problem with standard feed-forward networks. In a normal neural network, each input is treated independently. This works for many tasks, but fails when the order of data matters. Example, sequential data. A sentence is a sequence of words. To predict the next word, you need to remember the previous words. Similarly, sensor data over time, e.g., temperature, wind speed, wind direction, solar radiation, is a sequence. Why past data matters. Suppose we want to predict electric current or voltage at the current time t. Using only the current sensor readings might give poor predictions. But if we also consider past data, e.g., earlier temperature or wind patterns, we can make much better predictions. The solution, RNN. Recurrent neural networks are designed to remember previous inputs using an internal hidden state. This allows them to use historical information when making current predictions. So, let me explain how a recurrent neural network, or RNN, works. The basic idea is this. When we want to make a prediction at the current time step, let's call it time t, we don't have to use only the data we have right now. We can also use information from the previous hidden layer. That hidden layer came from time t-1, and it already contains useful past information. Here's how it works in practice. At the current time t, we have two things. First, the current input, for example, today's temperature or wind speed. Second, the hidden layer output from one step ago. That's the memory from the previous moment. We combine these two together, and we compute the new hidden layer for time t. Then, we calculate the output at time t using that new hidden layer. Why does this help? Because the hidden layer from t-1 already remembers earlier time steps, t-2, t-3, and so on. By reusing it over and over, the network effectively has access to all past inputs, even going back infinitely many steps. This means the network can capture long-term patterns in the data. In short, an RNN keeps a kind of memory, a hidden state that gets passed from one time step to the next. It uses both the current input and that past hidden information to make a better, more accurate prediction at the current moment. That's the core idea behind recurrent neural networks. Let's look at this slide. On the left, you see what's often called an Elman recurrent neural network. This is one of the classic ways to draw a simple RNN. Here's how it works. Input comes in from the bottom or the side. Then we compute the hidden layer. From that hidden layer, we produce the output. But the key point is this: the state of the hidden layer from one step ago is fed back into the network. That feedback loop affects the calculation of the hidden layer at the next time step. That feedback loop is what makes it a recurrent neural network. It's a simple way to incorporate information from the immediate past. However, this simple Elman RNN has a major limitation. It's not good at modeling long-term dependencies, that is, relationships between data points that are far apart in time.
Why?
Because when you try to capture information from many steps back, the network faces problems like vanishing gradients or exploding gradients. These are common issues in deep learning, where the gradient either becomes too small to learn effectively or too large and unstable. As a result, the network can't remember things from more than a few steps ago. So researchers asked, how can we solve this? How can we keep useful information for a long time without losing it or blowing it up? That led to an improved version called LSTM, which stands for Long Short-Term Memory. The main innovation in LSTM is the memory cell. Think of it as a special storage unit inside the network. It can retain information over long periods, and the network can learn to decide when to store new information, when to keep old information, and when to retrieve it. So, unlike the simple Elman RNN, LSTM can successfully model long-term dependencies. That's why it has become so popular for tasks like time series prediction, speech recognition, and natural language processing. In the next slides, I'll explain exactly how that memory cell works inside LSTM. Now, let me explain this recurrent neural network a little more concretely. First, let's look at the Elman type RNN. It looks like a normal two-layer neural network, but with a feedback loop, that is, the hidden layer from the previous time step is fed back into the current calculation. Writing it with lots of lines is messy, so instead we use vectors and matrices. The input at time t is a vector, xt. The hidden layer at time t is a vector, ht. The output is a vector, yt. The weights are also represented as matrices. U is weight matrix from input to hidden layer. W is weight matrix from previous hidden layer to current hidden layer. This is the loopback. V is weight matrix from hidden layer to output. Because the hidden layer is updated at each time step, we can write the hidden layer update formula like this. Here, h, t-1, is the hidden state from the previous time step. We multiply it by w, add the current input multiplied by u, add a bias b, and then pass everything through a tan h activation function. That gives the new hidden state ht. Then, to get the output at time t, we use another matrix v. Yt equal v multiplied by ht. So in summary, for an Elman RNN, the hidden state is updated using a simple formula, and the output is calculated from that hidden state. The feedback of the previous hidden state through matrix W is what makes it recurrent. That's the basic mathematical form. Now, let's look at a way to express the RNN that makes the time evolution of the hidden layer easy to understand. At the bottom, we have the input at time t, called xt. That input goes through a weight matrix U. From the left, we have the hidden state from the previous time step, h, t-1. That goes through another weight matrix W. We add these two together, pass them through a tan h activation function, and get the new hidden state ht. Then, to produce the output at time t, we take ht and multiply it by a third weight matrix V, giving yt. This diagram clearly shows how the hidden state evolves over time, feeding back into itself at each step. That's the basic RNN in a time-unrolled view. So, what makes LSTM cells so special? How do they achieve long-term dependency? And how do they know what information to keep and what to discard from memory? The answer is gates. As shown in the diagram, a typical LSTM cell has 3 special gates: the input gate, the forget gate, and the output gate. Now, I sometimes draw these diagrams expanded over time. When you expand it, you can see the time steps clearly. Here, we write the hidden layer state at different times. At time t-1, the hidden state is passed forward. To update the hidden state at time t, we do a few things. The input xt comes in and gets multiplied by a weight matrix. The previous hidden state h, t-1, also gets multiplied by its own weight. We add them together, apply a tan h activation, and compute the new hidden state ht. That's exactly the element type RNN, a simple recurrent network. But LSTM adds a twist. The twist is the memory cell and the 3 gates. These gates learn to control when to write new information into memory, when to erase old information, and when to output that memory. That's how LSTM can remember things for a long time and ignore irrelevant past data. So, while the basic RNN struggles with long-term dependencies, LSTM solves it with this gated structure. Next, let's look at how each gate works in detail. Each gate in an LSTM has multiple inputs. It's controlled by the state of the hidden layer. For example, let's look at the input gate. It takes 2 things: the current input vector xt and the previous hidden layer state h, t-1. From these, it calculates a gate value, a number between 0 and 1. That gate value then narrows or opens the flow of information. In other words, it decides how much of the new input should be allowed into the memory cell. So, the network learns, based on its current state and the input, whether to let that information in or keep it out. That's the basic idea. Let me explain in more detail next. Now, let's look at the 3 gates in more detail. First, the input gate. It controls how strongly new information is written into the memory cell. If the gate value is high, new input is stored. If low, it's mostly ignored. Second, the forget gate. This decides how much of the existing memory should be cleared or retained. A high forget gate value means keep the old memory. A low value means erase it. Third, the output gate. It controls how much information is pulled from the memory cell to the hidden state. This determines what the network actually outputs at the current time step. Each gate is computed using a similar formula. For example, the input gate at time t is. Here, xt is the current input, h, t-1, is the previous hidden state, and sigma s the sigmoid function, which outputs a value between 0 and 1, acting like a valve. Similarly, the forget gate ft and output gate ot have their own weight matrices and biases. These 3 gates work together to allow the LSTM to remember or forget information over long time periods. Next, I'll show you how these gates are actually used to update the memory cell and hidden state. In fact, this is actually an input network as well. Let's take the input gate as an example. The value calculated here comes from combining the current input xt and the previous hidden layer state ht-1. That combination goes through a logistic sigmoid function, so the output is a value between 0 and 1. That's the gate value. It decides how much new information to let in. Now, in LSTM, there is also a plus gate, and there's another neural network controlling that gate, and many other networks in different places. It has become a very interesting and powerful network. In this diagram, I've expanded the hidden layer state over time. We could also expand the memory cell over time, but that would make the diagram quite complicated, so I won't do that this time. Even so, you can see that writing it this way looks very complex. That's why recurrent neural networks, including LSTM, are often drawn in a much simpler, compact form. Here, we see a much simpler way to draw an LSTM. Basically, it's just a block, the LSTM block at time t. It has an input xt coming in and an output yt being calculated. It also has a hidden layer state ht, which is passed forward to the next time step, and the previous hidden state ht-1 comes in from the left. So the idea is, at each time step, the block receives an input and produces an output while updating its internal hidden state. What makes LSTM special is that inside this block, there's also something called a memory cell. The hidden state and the current input together decide how much to write into that memory and how much to read from it. That ability to control writing and reading, that's the interesting and unusual part of LSTM. Furthermore, this can be expanded over time and written like this. What kind of diagram is this? I write the same LSTM block at different times: t, t+1, t+2, t+3. If you write it this way, you can clearly see that the series information flows through the blocks. Each block receives an input at that time step and produces an output. And you can see the hidden states ht, h, t+1, etc., being passed from one block to the next. So, basically, in the case of LSTM, it takes in series data and outputs series data. Actually, these LSTM blocks can be used in many different ways. Next, I'd like to introduce some examples. The first example I want to introduce is prediction of series data, specifically forecasting future values. Take a look at this graph. It shows the monthly reported number of chickenpox cases in New York City from 1931 to 1972. This is quite old data, but it's a classic time series. The numbers are recorded month by month. Now, when we do machine learning on this kind of series data, we need to split it into a learning interval and a prediction interval. In this case, the first 90% of the data is used for training. The remaining 10% is held out for verification to see how well our model can predict the future. Using the training data, we train an LSTM to predict the next values in the series. That's the basic setup. So, what's the key point here? When we train an LSTM on this kind of series data to make predictions, what are the important things to consider? Basically, we are training the LSTM to predict one step ahead. Here's how it works. We input the data at time t, and the network learns to predict the data at time t+1. Then, when we feed in the data at time t+1, it learns to predict time t+2, and so on. So, using the training interval data, we constantly feed inputs into the LSTM, and we train it to produce outputs that are the next value in the series, one step ahead. Now, once we've successfully trained the network, what can we do with it? We can feed it a sequence of past data, and it will start predicting the future values, step by step. We can use it to forecast chickenpox cases or any other time series beyond the training data. That's the power of LSTM for series prediction. Here's the key idea. If you input the first data point, the LSTM can predict the next step. Then, you take that prediction and use it as the input for the next time step. By repeating this, you can predict step by step, many steps into the future. That's the basic method. Now, let's look at an example of network construction for time series regression. First, you define the layers, just like with convolutional neural networks. You start with a sequence input layer. The one inside means the input is one-dimensional. Next is an LSTM layer with 200. That 200 is the hidden layer dimension, the size of the hidden state. Then a fully connected layer. This is used to calculate the output from the hidden layer. Since we're predicting a one-dimensional value, we put 1 here. Finally, a regression layer is added. After defining the layers, you set the training options like the atom solver and maximum epochs, and then call the train network function. It's exactly the same process as when you train a convolutional network, so you can really do it the same way. Let me walk you through the code. First, we read the data from a CSV file called Chickenpox.csv. The first column is the year, and the next 12 columns are the monthly case numbers. We extract only the monthly numbers, then reshape them into one long column from January 1931 all the way to December 1971. We also create a timeline of dates, so we can plot it properly. Then we plot the data, the number of chickenpox patients per month over the years. You can see the seasonal ups and downs. Now we split the data. We take the first 90% of the total series as training data and the remaining 10% as test data. The training part will teach the network. The test part will be used to check how well it predicts the future. Next, we standardize the training data. That means we calculate its average and how spread out it is, the standard deviation. Then we subtract the average and divide by the spread. We do the same for the test data, but using the average and spread from the training set. This helps the network learn more smoothly. Now, we build the LSTM network. We start with a sequence input layer. The input is one-dimensional because we only have the monthly case number. Then an LSTM layer with 200 hidden units. That 200 is the size of the hidden state inside the LSTM. Then a fully connected layer with just one output, because we only predict one value at a time. Finally, a regression layer because we're doing a prediction, not classification. After defining the layers, we set the training options. We use the atom solver. We tell it to go through the data 250 times. That's 250 epochs. We set a gradient threshold to 1 to avoid the gradients exploding. The initial learning rate is 0.005, and we reduce it after a certain number of epochs using a piecewise schedule. We also ask MATLAB to show the training progress plot so we can see the error going down. Then we call train network, giving it the training inputs and targets, the layers, and the options. The training starts, and you can see the loss getting smaller over time. After training, we want to predict future values. First, we reset the network state and feed in all the training data to update the internal hidden state. Then we take the first test input, that's the first month of the test period, and ask the network to predict the next month. For the second step, we take that predicted value and use it as the input to predict the next month, and so on. We loop like that for all the test steps. When we get the predictions, they are still in the standardized form, scaled. So we multiply by the original standard deviation and add back the original average to get real patient numbers. We calculate the root mean squared error, RMSE, to see how far off the predictions are from the true test values. Then we plot the observed data and the predicted data on the same graph so you can see how well they match. We also make another graph showing the prediction errors as vertical stems. Now, let's look at this second part of the code. First, we reset the network state. That clears any old information left over from previous runs. Then we feed in all the training data again, but this time we only update the state. We don't collect predictions. This prepares the network, so its hidden state and memory cells are set to the end of the training period. After that, we create an empty variable to store our predictions. We find out how many test time steps there are. That's the length of xtst. Now we enter a loop. For each test month, we take the actual observed value from that month, xtst, and call predict and update state. This does two things. It predicts the next month's value, and it updates the network's internal state using the real observation we just gave it. So the network always gets the true data, not its own previous predictions. We store each prediction in ypred. Once the loop finishes, we reverse the standardization, multiply by the standard deviation, sig, and add the mean mu to get back to real patient numbers. Then we calculate the root mean squared error between our predictions and the actual test values, and we display that number in the command window. Finally, we make a figure with two subplots stacked vertically. The top subplot shows the observed test values in a line, and our predicted values as dots connected by lines. That lets us compare how well the predictions match reality. We label the y-axis, number of patients, and give it a title. The bottom subplot uses a stem plot, those vertical lines with circles on top, to show the prediction error, which is predicted minus observed. The title includes the RMSE value we computed. So this part essentially tests the LSTM in a real-time mode. At each month, it gets the true observation, updates its memory, and predicts the next month. That's different from the earlier method where it used its own predictions as inputs. Thanks so much for watching. If you found this helpful, hit that like button, and don't forget to subscribe so you don't miss the next deep dive into AI and deep learning. See you in the next video.